supporting force for the roadway. In a problem like this, which like I said, I'll call this the bridge question. There's the qualitative and the quantitative. I want you to imagine that a vehicle makes it onto the bridge and is going to drive across the bridge. And the vehicle has mass M, and the bridge, its span has mass capital M. Now, this first thing I'm going to say, I think is obvious, but there's a lot of things that I think are obvious that you don't. But there are two normal forces that act on the bridge. One here and one here. At this moment, if I was asking you to figure out the size of the normal forces, using force wouldn't be enough. Because truthfully, there's the normal force on the left and the normal force on the right. And there's no reason to believe they are the same. I do know that the normal force on the left plus the normal force on the right has to equal the weight of the bridge and the weight of the car. I know that has to be true. But as the car drives across the bridge, the weight of the system doesn't change. But is it clear to some of you that when the car is all the way on the right, this pylon probably supports more of its weight? And when it's all the way on the left, this pylon probably supports more of its weight? The issue is that this kind of problem can't be solved by looking at force, because force doesn't give me enough information. This kind of problem requires that it be solved looking at torque. This is a statics torque question. And I want to talk about how we solve static torque questions. A static torque question is one in which we don't believe the system is going to move, or we don't believe the system is going to rotate. That's what a static torque question is. Now, I know it sounds different than what I said. The car's moving. But ultimately, what we're not focused on is the car, but the bridge. The bridge doesn't move. And because the bridge doesn't move, we say the bridge is in static equilibrium. That means two things. One of them you already know. The net force is zero. What is it that we're introducing today? So what do you think I'm going to say about the torque? The net torque is zero. That's right. In these kinds of problems, the net force and the net torque is zero. Now, look, there's the qualitative part and the quantitative part. The qualitative part is you knowing that the car's presence on the bridge determines how much of the normal force is being distributed on each of the pylons, and that the normal force will be greater when it's closer to a pylon. The only time the normal force will be equal is when the car is in the middle of the bridge. What's interesting is that when the car is off to one side, this probably has more normal force than the car and its share of the bridge. Meaning, has anybody ever kicked up a skateboard before? Kicked it off its front wheels? Does anybody know what I'm talking about? If I push down hard enough here, what's going to happen over here? So it is possible that if the car were heavy enough, this normal force could disappear because the bridge would tip over this way. So don't assume anything. Don't assume there has to even be a normal force over here. That's the first thing I need you to have in your notes. The first thing that you should study. It's a condition. And condition problems are hard for you guys. But this system becomes dynamic if you push hard enough on one side. you can cause the bridge to rotate. One question I might ask on a test would be to put like A, B, C, D, E, and ask where can I press down and have the bridge lift up? And hopefully most of you would say the only place that I've listed here would be A. It's possible I push down hard enough at A, the system could lift up. That kind of qualitative question needs to be something you can solve. Also, I could put the car here and say, something like which normal force is the smallest when the car is located at, and pick a place. Those kinds of qualitative questions you need to be able to answer. Let's do the qualitative one, though. I'm going to put some numbers to this. I'm going to actually put the car someplace in the problem. So let's go ahead and put the car someplace meaningful. First, give me a mass for the car. 5. Okay, so the car is 1,000 kilograms. Mass of the bridge. 10,000? Okay. It's not great. It's a lot of zeros, but okay. 10,000 kilograms mass of the bridge. And let's go ahead and say the bridge is 100 meters long. And that this is, let's go with 10 meters. And this is 10 meters. But the bridge is 20 and 20. It'll work out better. 20 and 20. But the bridge is 100 meters long. And let's say that the bridge is uniform. So its center of mass or center of gravity is at its middle, which means its weight is 100,000 newtons. And let's say the car is 10 meters away from the first pylon. Now, there's a lot of ways these problems can be set up. This is one of them. We're going to find both normal forces. That's going to be our question. Determine both normal forces. Now, there are two parts to this problem, the force part and the torque part. And it doesn't matter which one you do first. And I'm not going to spend a lot of time on this because it's really not a huge curricular point. I'm going to tell you a series of things you should do to make your problem go quicker. First, you know how to do the force part. I don't believe I have to do anything there to help you. In this problem, the force part is net force equals 0. So this moment, you should be able to say the normal forces add together to equal 110,000 newtons. The car's 10,000 newtons. The bridge is 100,000 newtons. Any question about that stuff? All right, that's the pretty easy stuff. So the first part is to do the force problem. In a torque question like this, you'll know that you need to use torque because the force problem will leave you something that you cannot solve. Right? We can't solve for one of the normal forces. We don't have any more information. Now, I know we've done force problems before where it seemed like we could get the answer. I've chosen ones where we could. This one, purposely, we can't. Now, it might not be obvious that torque is the way to go, but any problem that is at rest could be a net torque question. So it's worth looking at. So we're going to do the torque part of this problem now. And this picture's a little bit clouded and cumbersome. I want to get to a screen that's a little bit more clean. Is that all right? So I'm going to clean this up. But we're going to come back to this in just a minute. Right? We know it from here. That I don't have to do another torque problem. I just have to subtract. And when I subtract, I'll know what the other force is, which I'm pretty sure is 51,667. I just want something that has just the bridge in it. When we go to handle a torque portion of the problem, it's almost always easier to start with a nice, clean picture. We can't do a free body diagram like we used to anymore because where the forces apply make a difference. So I tentatively draw the shape of the object that could rotate. In this case, the bridge. And then on the bridge proper, I draw in all the forces as they act on the bridge. For example, there is a normal force acting over here, NL. The weight of the bridge is right here at the middle, 100,000 newtons. There's another normal force over here, NR. And then there's the weight of the car, 10,000 newtons. Now, this is the part that's hard for students to do, so let me just tell you the best way to go about it. Problems that have no fixed pivot point. And you should like highlight this or square it. Something that makes it bold. Problems that have no fixed pivot point. Either pivot about the center of mass or, and this is the important part, if they're static, you can pick the pivot point. I know that's a whole lot, but we need both of those pieces of information. So again, objects that have no fixed pivot point, either pivot about their center of mass, or if the problem is static, you can choose the pivot point. Now, the reason why I need to give you both parts is that you're going to get a problem where like a bat hits a ball in space. What happens to the bat? The bat spins away. And they're going to ask weird questions. They always will rotate about their center of mass if there isn't a fixed pivot point. But static problems are different. The bridge doesn't have a fixed pivot point. But it's static. It doesn't actually pivot. So you may choose your pivot point. Now, this next part isn't a hard and fast rule. It's what I would do if I were solving the problem. It makes it easier. Always put your pivot on an unknown force. If the problem is static, always put your pivot on an unknown force. Okay, we have two unknown forces. It does not matter which one of these we pick. We know they add up to be 110,000 newtons. We know that's what they add up to be. As long as we can figure out one of them, we can figure out the other. We just need one of them. So you can pick either the left one or the right one to be our pivot point. Which one do you want to choose as our pivot? So if our left one is the pivot point, I'm going to clearly articulate the pivot point by putting a caret in there, a little triangle. Then I'm going to indicate on the diagram the direction that is positive. Your book wants counterclockwise to be positive. I'm going to stay consistent with the book, mostly so you'll get the mastering right. All right? The mastering wants counterclockwise to be positive. I really couldn't care less. It's like saying up is positive, though. Lots of people agree with it, so they just go with it. Now, how many torques are in this system? Once we choose the pivot, we determine the number of torques based on where the pivot is. How many forces are being applied somewhere away from the pivot? 3. There are 3 torques in this problem. Is the object accelerating? No. There are 3 torques in the problem, and they're going to add up to be 0. I will always write out the problems like this. I'll go through, figure out how many torques there are, and I'll set up a stack like this and remind myself that in this problem they add up to be 0. And looking at this, there's the torque from the bridge, there's the torque from the car, and there's the torque from the other normal force, the 3 torques that are in this problem. Now, every torque is going to be plus or minus the torque arm length, the force, and the sine of the angle. So every torque has to have all 3 pieces identified, and then decide if it's plus or minus. So we'll start with the bridge. In order for us to use this as our pivot point, we need this distance, because that's the torque arm length. The whole bridge is 100 meters. Take a second and figure out what that distance is. I'm picking on one of you to tell me. This is me figuring out whether you're paying attention or not. And you have 10. What is that distance?
30 meters.
30 meters. Thank you very much. So 30 meters. We already know the force. It's 100,000. You know, I didn't do a great job of leaving space here, so there. The force is 100,000 newtons because it's the bridge. Can we all agree it's straight down and the bridge is horizontal, so it's a sine of 90, just like your lab? Now you have to figure out whether that torque is positive or negative. Think about it. I'm about to call somebody. And Hogsmeade, positive or negative? So you have to ask yourself, will this force cause the bridge to rotate this way? Or will it cause the bridge to rotate this way? All right. Do you understand why it's negative?
Yes.
Okay. So it's negative. Great. All right. We did one of them together. You guys do the other 2. I'm going to call on 2 people in the room. They will tell me what the other 2 torques are. You have 30 seconds.
50 meters times 10,000 newtons times sine 90.
I 100% agree with you. Fantastic work. Thank you very much. The last one is going to give me by somebody who sits where the triangle is. Where's the triangle? Raise your hand, triangles. It is triangle Earth. Who's that? All right, James, bring it.
I was having trouble figuring this one out because of the force. I know it's at least positive.
Okay, good.
The radius, I'm pretty sure, is 50. No, it was 60.
That's right. It's 60. You're doing great.
And then I'm pretty sure the sine theta was 270 degrees.
Sine will just be 90.
90, okay.
I don't ever deal with any angle for torque greater than 180. I'll let positive and negative deal with itself through observation. Does that make sense? So don't go 270 because that's going to give you a sign that's negative that could inadvertently affect your problem. In this particular case, this force is upwards, causing a twist of this system in that direction. We've already identified that as the positive direction. What is the force that is causing this torque?
It's the normal force from the right pylon.
That's it. All right, remember, we're looking for normal force. That's what we're trying to find, is the normal force. It is the one unknown. Okay, look, that's it. Do you guys see that's all you have to do? I mean, I'm not saying that's easy. I'm saying it's very pragmatic. Go force by force through your diagram, find out where they act and what direction they act and what angle they act. Yes, sir.
So why is it sine 90 for the last one? The other ones are sine 90 and they're going down, but the last one's going up.
The angle is the measurement between the torque arm and the applied force. So the torque arm is running through this bar this way.
So it doesn't matter like which way
No,
okay.
that part doesn't matter. We are dealing, all that would do, if we did 270, let's figure out what would happen. If we did 270 here instead of sine of 90, it would make -1 and a +1. So how many different ways do we want to use to tell us that the torque is positive or negative? We could use exclusively the angle, but then we'd have to measure them all relative to the same direction. Even torque arms are on the other side. That begins to become very cumbersome. So I would always go with the smallest angle. And you'll never go wrong if you determine direction yourself. Okay, so we can finish this problem. I want to, but do you realize that there's really not a whole heck of a lot left to do? You're just going to add all those things together and set them equal to 0. So let's just look at what that is going to entail, and then we can move on. I'm going to have 30 times 100,000, which is 3 million, and it's negative. I have 50 times 10,000, that is 50,000, and it is negative. And I have 60 times NR, which is 60 NR, and that equals 0. Yep,
Shouldn't 50 times 10,000 be
500,000. Sure. There we go, 500,000. No commas though. It'll be okay. So this is now a calculator problem, and I don't really care what the answer is. I know that we can write it as 350,000 divided by 6, which when I do math is less than, well, it's going to be less than 60,000, but not much. 50 what thousand? Somebody had to have done it. Really, nobody?
58,000?
I don't know. It's not going to be even. It's going to be something, with a non-repeating, non-terminating decimal. 333?
58,000.
There we go. All right, so that's in newtons, because it's a force. And we're done, because we know the left-hand pylon. Notice the right pylon, more the weight than the left. Not a surprise. Now, you guys, it wouldn't have mattered if we had chosen this as our pylon. It would have given us the same answer. I'm sorry, that is our pivot. It actually wouldn't have mattered if we chose this as our pivot, but if we chose the middle one as our pivot, we would have had 2 unknowns. That would make it harder. So this is a statics problem. I'm going to show you 2 other ones. We're not going to work them out. I just want you to see what they look like and the bridge. And I'll provide you with a couple of examples as we go. Another statics problem we've done already once, but I was very careful about how I talked about it in class. Remember the problem where we had like 2 ropes holding a box? Do you remember those? Well, those are to replace a problem like this. So I have like a building, and there's a boom arm here, and that boom arm has a mass on it over here. You should be able to identify all the forces that act on the boom arm. That's what this is called. This is called a boom arm. Can you identify all the forces? I would strongly encourage you not to underestimate this. I'm asking because you will get this wrong. So please identify the forces that must act on this. Because there are 5. And most people don't realize that. That means 5 of you I get to call on. All right, ready? Check with the person around you, make sure. There's 5, for sure. For sure. 5 arrows. All right, here we go. Paradise Falls, give me 1. That's you guys. Tension. That's a nice, easy, low-hanging fruit. Way to go. There is a rope applying tension right there. Excellent. Halo array. Give me another one.
Is there another tension for the holding block?
Sure. Tension over here. I'll call that tension for the mass. This is tension for a cable. Excellent. Thank you. Winterfell. Give me another one.
Weight
Weight of what?
of the box.
The box? Is that what you said?
Yeah.
Okay, that's actually involved in the tension. If the net force is 0, this would be the weight of the box. You got another one?
The weight of the boom.
The weight of the boom arm. Assuming it's uniform, it acts at the center. So sure. All right, there are 2 more. This is where we really separate out the smarties from the non-smarties. Bikini Bottom, do you got one for me? I would say the normal force of the building on the boom arm. And I'd be okay with that. That's right. That's another force. Good one. Yeah, without that one, the boom arm crashes through the building. Now, this next one's hard, and I don't know if anybody's going to get it. So I'm not going to call on the table. Does anybody want to venture a guess? Go ahead.
Does the weight of the building count?
Nope.
As part of the system?
It's its own system. There are forces that act on a boom arm. They are separate from the forces that act on a building. Paige, go ahead.
Would there be friction on the boom arm and the building going?
That's right. Well, there's normal force. There's a possibility of friction. There's got to be something that keeps the arm from sliding down the building. Excellent. Or sliding up the building. We don't really know. It pivots here, perhaps. And it could slide up the building. We don't know. That's why we analyze this. And that's why whenever you guys will eventually own your own homes or own your businesses, that's why you have to pay permits for contractors to make decisions about this stuff, because if you do it and break something, you could be liable. All right, so that is the standard boom arm problem. You can see all the little stuff here that could be designed to trick you up. Angles like, being thrown in to mess this up, stuff like that. But this problem is more about you thinking some things through. Like, if the wire wasn't particularly strong, would you want to connect it here or out here? Which would require less tension? And some of you might know why this is, and some of you might not. This is why we talk about problems like this. But there's less tension the further away we connect this particular thing, because it's a bigger torque arm. So you can apply less force. The closer we get, it's going to have to be more. This problem comes in two forms, by the way. There's this one, and here translates similar way as this. And there's one that you probably won't recognize when I draw it like this, but it is one that is a big favorite because it's biological. So forearm, bicep, hand. So you put a weight in your hand. The bicep muscle. Hey, be nice, I know. Oh, I better not write that. This arm. The bicep muscle actually has a point of insertion here. It's funny because we tend to think about strength in odd ways, but a lot of apes are stronger than us, not because their muscle fibers are stronger, but because of where their muscles attach to their bones. If you move the insertion point out, two muscles of the same strength can do different things because they have a larger torque arm. But this kind of problem, this is why people shatter elbows all the time too. Recognizing that you might not be infinitely strong. But the human body is a great machine. The problem we just directly to this problem. So there are lots of ways and reasons and stuff that they can do for torque. And they will talk about this kind of stuff on the test. We have to be prepared to deal with that. All right. That's enough about statics. We are going to mix a bunch of static stuff in with our work a little at a time, but I wanted to make sure it was introduced to you. These are static style questions. Your next test will have qualitative questions that will be structured, but the thing I would like to talk to you a little bit more, and it's going to take today and most of tomorrow, is moment of inertia. Static questions never involve the moment of inertia. And here's why. The moment of inertia is only an issue if your object is accelerating or moving. The moment of inertia only shows up when inertia shows up. So inertia never showed up when the net force was zero. Inertia only began to show up when the net force wasn't zero. So the same with torque. With torque, net force didn't show up. Inertia didn't show up when the net torque is zero. But when the net torque isn't zero, then there's an acceleration. And the amount of the acceleration is dependent upon the moment of inertia. We talked about this last week. Today we got to be a little more specific. We use a capital I for the moment of inertia. We didn't talk about that last week. But the moment of inertia is capital I. It's pretty standard. It's on your equation sheet. Last week we talked about what the moment of inertia is. It is a measure of the distribution of the mass about the pivot. And you could also say it's rotational inertia. I got three definitions here. So let's go through all three of them. It is the distribution of the mass about the pivot. That's technically how we find it. So remember, the closer the mass is to the pivot, the smaller the inertia. Second, it is the rotational inertia. Third, it is how difficult it is to twist or turn an object. You could say it's the resistance to torque. In the same way that inertia was the resistance to force. All right, so now you have to deal with the technicalities. The technicalities of calculating a moment of inertia. You will have to do two different kinds. You'll have to deal with the point mass calculation and smooth or rigid objects. Two different kinds of moments of inertia. You'll never have to prove what a moment of inertia is unless it's a point mass. Now, I know what you're thinking. What do I mean by point mass? Or point mass? Point masses would look something like this. And this is what was in your homework. There were 3 heavy spheres connected by 4 light rods. This is in your homework. So 4 heavy spheres connected by 4 light rods to a central spindle like that. This is a classic way that a point mass is laid out. Point masses are just that. Anytime an object can be considered to be made up of small, precise masses, where the mass can appear to be concentrated from some point rather than some distribution. Before you walk out, you got to write this down. For a point mass, it is the sum of the mass times the distance to the axis. Just get that in your notes so at least I know where we ended. All right.